How geothermal pumps work. With about 3.7 gigawatts produced annually, the United States is the world leader in geothermal electricity production. That would power over 2.7 million houses in the United States. Ever wondered how geothermal pumps work? Well, you're in for a treat. In today's video, we'll uncover the secrets behind these incredible machines. But before we get started, if you're new here, don't forget to hit that subscribe button and ring the notification bell so you never miss out on our exciting content. First things first, what exactly is geothermal energy? It's the heat from the Earth's core that we can tap into and use to generate electricity or heat our homes. Imagine having access to a boundless, renewable energy source right beneath our feet. But how do we harness this incredible power? That's where geothermal pumps come into play. Let's jump right in. Now, here's the magic. Geothermal pumps work by leveraging the consistent temperature of the Earth just below the surface. The Earth acts as a natural heat exchanger. In winter, the fluid absorbs heat from the ground and brings it into your home, keeping you warm. In summer, it does the opposite, pulling heat from your home and depositing it into the cooler ground. It's like having your own temperature-regulating superhero right in your backyard. The geothermal heat pump system comes with various options on how to tap into this natural reservoir of heat. We will discuss open and closed loop systems, horizontal versus vertical systems, and when to use them. In addition to the yearly energy savings, a geothermal heat pump system is more expensive than a conventional heat pump system, although this difference can be offset by potential incentives and rebates. Warm air from inside the structure is introduced into the ground source heat pump when it is in cooling mode. Warm air will be absorbed by the heat pump's inside coil and circulated through a cooled liquid refrigerant. Refrigerant will boil and convert into a gas when it absorbs the heat. The cooler water that is moving through the system from below ground will absorb the refrigerant as it moves through the system. After being absorbed by the water, the heat is then rejected to the colder ground underneath. The second law of thermodynamics states that heat transfers from a warmer to a cooler object. Keep this in mind. There is never any contact between the refrigerant and the water. The opposite happens in heating mode. The second law of thermodynamics states that we must always follow the heat. In this instance, the Earth provides the heat. After being circulated, the chilly water absorbs heat from the Earth below. Following its circulation into the ground source heat pump, the warm water is absorbed by the refrigerant, causing the liquid to boil and evaporate. After that, the heated refrigerant is moved to the indoor coil, where it interacts with the space's colder return air. The departing supply air gets heated as a result of the cold return air absorbing heat from the hot refrigerant. Buildings can be heated and cooled with the use of heat pumps. At a depth of roughly 30 feet below the surface, the temperature consistently ranges between 50 and 59 degrees Fahrenheit throughout the year. With the help of these steady subsurface temperatures, geothermal heat pumps effectively exchange heat, heating and cooling buildings throughout the year. A geothermal heat pump employs a network of interconnected pipes buried in the ground close to a building to use the Earth as a heat source and sink. Thermal storage. Either a vertical or horizontal burial is possible for the loop. It moves a liquid that, depending on whether the ambient, outside, air is warmer or cooler than the soil, either absorbs or deposits heat into the surrounding soil. A geothermal heat pump collects heat from the fluids in the collector, concentrates it, and transfers it to the building when the outside temperature is lower than the Earth. The heat pump extracts heat from the structure and stores it underground when the outside air temperature is higher than the ground. The geothermal heat pump's heated or cold air is often distributed throughout the structure using conventional ducting. The three primary technologies used in geothermal power plants are binary cycle, flash steam, and dry steam. The kind of conversion, which is determined by temperature and the condition of the subsurface fluid, steam or water, is a component of the design of the power plant. Dry steam plants utilize use of hydrothermal fluids, which are very uncommon in nature, and are already primarily steam. The turbine that powers an electricity-producing generator receives the steam directly. Steam is often re-injected into the reservoir after it condenses. The earliest kind of geothermal power plant is a dry steam system, which was implemented at Lardarello, Italy, in 1904. Steam technology is still important today and is currently in use in Northern California at the geysers, the world's largest single source of geothermal power. Next is flash steam power. The most prevalent kind of geothermal power plant in use today is the flash steam plant. Pumped from deep underground, fluids with temperatures higher than 182 degrees Celsius / 360 degrees Fahrenheit flow under high pressure to a low-pressure tank at the surface of the Earth. A portion of the fluid flashes or quickly turns into vapor due to the pressure difference. After that, the vapor powers a turbine, which powers a generator. To extract even more energy, any liquid that is left in a low-pressure tank can be flashed again in a different tank. Because binary cycle geothermal power plants may employ lower temperature geothermal resources, they are a crucial technological advancement for expanding the usage of geothermal electricity production. The geothermal reservoir fluids of binary cycle geothermal power plants never come into contact with the turbine units of the power plant, setting them apart from dry steam and flash steam systems. Geothermal fluids with low temperatures below 182 degrees Celsius / 360 degrees Fahrenheit pass through a heat exchanger along with a secondary fluid or binary fluid. Because this binary fluid has a significantly lower boiling point than water, it flashes to vapor when exposed to the geothermal fluid's mild heat, spinning the generators and driving the turbines to produce energy. And there you have it. The fascinating world of geothermal pumps unveiled. From understanding geothermal energy to the magic behind these pumps, we've covered it all. If you enjoyed this video, don't forget to give it a thumbs up and share it with your friends. And if you have any questions or topics you'd like us to explore, leave a comment down below.